All right, let's try another interesting one here. I would describe this one out of chapter 4 of the college physics, but it's actually a problem in chapter 5 because it's the beginning part of Newton's second law. And so it's problem number 80, and I printed it up here. It looks a lot like the 79 here. And problems like this, as I said, 4 steps. Get a good physical picture of what's going on, draw the free body diagram, write out the equations, and then solve it. And those are kind of the 4 big steps. And on this one, like 79, they really haven't given us a physical problem to focus on. So we really can't kind of accomplish that. In the free body diagram, they've already done that. So we'll just start writing out the equations, and they even give us a grid to do that. So it says a body of mass 2 kilograms is moving along the x-axis with a speed of 3 meters per second at the instant represented below. All right, so this thing's already moving. What is the acceleration? Now, I'll just point out that the acceleration is irrelevant to the fact that it's already moving. The sum of the forces determine the acceleration. The acceleration has nothing to do with how fast it's going. So clearly the acceleration is then going to change that speed, but has nothing to do with the speed. So I'm going to go ahead and start this problem then by dividing my paper into x and y. And looking at these forces, I have a feeling I'm going to have an acceleration in both x and in y. And that probably will come into play in B and in C. All right, so I'm going to add up the forces in the x direction and set it equal to mass times acceleration in the x direction. And likewise, I'm going to add up the forces in the y direction and set it equal to mass times acceleration in the y direction. Now, as you've seen me do a couple of times, I'll put the equal sign. Well, I hope I left myself enough room. And I'll put an equal sign here. But the mass is 2 times acceleration x. And so over here, I'll go 2 times acceleration y. But what I really want to point out is I'm just going to go through and go to each of the forces, and I'll do them in order 1, 2, and 3. And each time I'm going to say, what is the x and y component, and put it in the appropriate spot here, because this says add up all the forces. All right. So let's look at force number 1. You'll see it is over to the right and up. So that means for x, it is positive. I guess it also means for y, it is positive. Now for x, if I kind of view this little piece as made up of a horizontal piece and a vertical piece, I would want the piece here for x, right here, adjacent to this angle of 37. So it is the cosine function that gives me the adjacent. So if I take the hypotenuse, and multiply it by cosine of 37, that would give me my x component. And then over here, if I take the hypotenuse and multiply it by the sine of 37. Oh, this looks like the magical 3, 4, 5 right triangle, except the 5 has been multiplied by 10. So this would be 30, and this would be 40. Anyways, let's not worry about the math here quite yet. But that would be the x and y components. Now let me move on to force number 2. And maybe draw it in green. I would say force number 2 is down and left. So the down would mean a negative for the y, and the left would also mean a negative for the x. Okay. Now, to get, say, the x component here, I want this piece, which is opposite of the 30. And opposite is the sine function. So this should be sine of 30 degrees. And then times the hypotenuse, which is 30. Oh, good. They gave me another easy one because 30 times, that would be a half. That's 15. Again, I shouldn't worry about the math. Okay, so then minus, okay, and the y component would be adjacent to the 30. So this is going to be cosine of 30, and then the hypotenuse is 30. And this I'll really need a calculator because that would be 0.866 times 30. All right, and then finally, let me go to the last force, number 3. And they're showing it all in the negative x direction. So I would put over here in the x negative 80. And over here I'd put plus 0. There's nothing in the y direction. But again, it's kind of nice to write each of these showing you what I have done is add up all the forces, all 3 of them. And each time for each force, there's an x and a y component, even if it's 0. It's kind of boring, but I think maybe to help your education, I'll put the 0 here. All right, well, then I have all these, and I can actually solve then for the acceleration in x, and I can actually solve for the acceleration in y. So let me do that. And as I said, this would be 50 times cosine of 37. That's got to be close to 40. Okay, there's 40. Then minus 30 times sine 30. That's going to take away a 15. Let's see, 40 take away 15 is about a 25. Okay, so we're at 25. Then minus 80 gives me a negative 55. So negative 55, and I'll call it a 1. Oh, and then divide by 2. Sorry. Forgot that important last step. Divide by 2. All right, so that is a negative 27.5 for the acceleration in the x direction. Okay, now let's do the same math here. This 50 times sine of 37 must be about 30. Okay, good. Minus, and I can't do this one in my head here, so 30 times cosine of 30 and plus 0. And so that's 4.1, and then divide by 2. And so there is a small 2.05 acceleration in the y direction, at least small compared to what it is in the x direction. So you could think of the combination of these 3 as being quite a bit in the x, and really most of it comes from number 3. 2 is kind of contributing to it, but 1 is taking that away, and then a little more. But most of this is coming from force number 3. Well, if it was only 3, that would come out to be a 40, and we're kind of short of that. Anyways, but that's acceleration x, and that's acceleration y. And then it's positive, okay? So that's kind of the first answer to this. What is the acceleration of it? And I've left it in x and y purposely because look at the next part. B, what is the body's velocity 10 seconds later? So leaving the acceleration in the x direction and the y direction alone allows me to then write out the velocity final in the x equals initial velocity x plus acceleration xt, and final velocity y equals initial velocity y plus acceleration yt. So that's our first kinematic equation, and we can apply it to a problem like this because we're saying it has a constant set of forces resulting in a constant acceleration. So this object said it was already moving at a speed of 3. And of course, then it has an acceleration of negative 7.5. If it had that acceleration, a pretty big acceleration, for 10 seconds, that would be a negative 275, taking away the 3. So the initial speed of 3 is part of the problem, but kind of boring, minus the 27.5 multiplied by 10, giving me a speed of negative 272 meters per second. So this large acceleration would slow it down. It wouldn't even take but a fraction of a second for it to come to a stop in the x direction and then start racing back the other way. This one's a little more boring. I think they're implying that it has no speed in the y direction because it just says it's along the x-axis at a speed of 3. So I'm going to say the y speed is 0. The acceleration, as we worked out, was the 2.05, and so if we multiply it by 10, we're going to get 20.5 meters per second. So this thing will be moving to the x very quickly and a little bit up after these 10 seconds. And then, of course, C, I'll fit that on here, would be, say, what is its displacement? Okay. Well, again, since it's a constant acceleration, I'm going to put x equals to x naught plus the initial velocity times t plus 1/2 at squared. The displacement is the difference between where it is now and where it started. So I can just put in my 3 for 10 seconds, my 1/2. The acceleration is that negative 27.5 and 10 seconds squared. So the 3 times 10 is the 30. Let me just put the minus in the calculator already. 1/2 times the 27.5 times the 10 squared equals. And so this has got a pretty good distance, well over a kilometer. It's 1,345 meters in the negative direction. And it makes sense. It's going pretty fast after 10 seconds in the negative direction. Had a big acceleration. So not only did it stop it in the forward motion, but it made it go backwards quite a bit of distance, 1.3 kilometers. Now, applying that same equation for the y direction, would get me how far does it go on the y. And so here's the final minus initial for the y. This one I'll just cross out because the initial velocity in the y is 0. And so then I just have 1/2 and an acceleration is 2.05 for 10 seconds squared. So not much of an acceleration, which isn't much of a speed. So it probably doesn't go very far, but it's worth noting that it would go in the y direction just over 100 meters. So again, most of the motion is x, some in the y. And since they say displacement, maybe I can leave them there. But if I squared them and did the Pythagorean Theorem, it'd give me the total distance. So it'd be this direction, 1,345, and up 103. And maybe just get a number. I'll kind of do that. So 1,345 squared added to 103 squared, and taking the square root is 1,349 meters from where it started. Yeah, and they do say displacement, so I think they want beginning minus and t, x and y, not them separately. So maybe I should come back here and say, well, The magnitude of this velocity then would be 272 this way and 20 that way. So doing Pythagorean's theorem, 272 squared plus 20.5 squared, enter, taking the square, taking the square roots, is 272.8. So again, most of it is x. It's the whole speed is just something very much bigger, barely bigger than just x. All right, hope that one helps.